Hello, welcome to this supplementary session to the Spherical Astronomy talk series. In this session, we are going to go over the concepts that we discussed in part 1 of the Spherical Astronomy talk series using Planetarium software. So we will simulate some of these concepts and understand them. The Planetarium software I'm using is called K-Stars. It's near and dear to my heart because I'm one of its contributors, and so I kind of know the software pretty well, and that's why I'm choosing to use it. So currently the software is simulating the sky as you would see right now from Bangalore, India. Right now it is 6 a.m. in Bangalore. That is the LT here, local time. The UT line here shows the universal time. Remember, that's the same as Greenwich Mean Time for practical purposes. And the Indian Standard Time, which is a local time in this case, is offset by 5.5 hours from the UT. Remember that the first step in doing any astronomical calculation is to convert your local time to UT. So that's why we are seeing the UT here. ST here is the sidereal time, the local sidereal time, and we'll get back to that later. JD stands for Julian Day. We have not covered this concept, and it'll be part of the second part of the talk series. Okay, so currently we are looking at the north side of the sky, and there's Cassiopeia and so on and so forth. Here's the pole star, where my mouse cursor is pointing right now, and so the pole star is above the horizon, and because we are in the northern hemisphere, and its altitude is equal to the latitude of the location. Okay, this green part, shaded part, is the ground. So that's the part of the celestial sphere that we cannot see because it's below the horizon. If I can turn it off because this is software simulation, but this line here is the horizon. You can see the sun is just about to rise in Bangalore. This green line, the faint green line you're seeing here, is the horizon line. Okay. Now let me turn off the ground. Or turn on the ground again, so we can only see the part of the sky that we can actually see. And let me turn on the alt-azimuth coordinate grid. Remember, we discussed that there are these things called horizontal coordinates, which are altitude and azimuth, and also known as alt-azimuth or topocentric coordinates. So we'll now talk about that coordinate system. The coordinate system has a pole. This kind of point is called a pole at the zenith. By that I don't mean the north pole or the north celestial pole or anything. I just mean the pole of the coordinate system where all of these meridians meet. That's in this case the zenith or zenith. And the dashed lines here are meridians of fixed azimuth. So they are the lines of constant azimuth. They are great semicircles. We discussed this in part 1. So the other circles that you are seeing here are circles of fixed altitude. They are not great circles except for the one with altitude equals 0. That's the horizon circle. The rest are not great circles. Whereas all the meridians of azimuth are parts of great circles. They are great semicircles. Okay. Now every coordinate system used to describe a spherical geometry, right? Like either the sky or the earth and so on, has two poles. Like for the coordinate system on earth, the two poles are the north pole of the earth and the south pole of the earth. And every such coordinate system has one of these longitude-like coordinates, which forms great circle or great semicircle meridians, and it has one other coordinate which is a latitude-like coordinate, and that forms circles around the poles. Okay, in the case of the horizontal coordinate system, the latitude-like coordinate is the altitude, and the longitude-like coordinate is the azimuth, and the poles are the zenith. The other pole is below the horizon. We can never see it because it's it's exactly below your feet, like opposite of the zenith, and that's called the nadir. It is down here, right? That is the other pole of this. So I've turned off the ground and gone below the horizon to show it to you. So most of the time we only concern ourselves with the zenith. Okay. So remember, we picked the convention. Now I moved back to the northern part of the sky. So N for north here. Remember, we picked the convention in the talk series that the azimuth of the north will be 0 degrees. K-stars also follows the same convention. So you can see over here that this line corresponds to 0 degrees azimuth. I forgot to mention, this status bar at the bottom right, where my mouse cursor currently is, this shows the coordinates of my mouse cursor when my mouse cursor is on the map. That's a useful feature. So when my mouse cursor is on this line, the first coordinate here, which is the azimuth, is very close to 0. So the coordinates here are azimuth, altitude, right ascension, and declination, right? And so when I'm in the north, this azimuth line here corresponds to 0 degrees of azimuth. Okay. So now we have discussed the alt-azimuth coordinate system. No matter where in the world you are, the zenith is always the point that is vertically above. Okay, so the horizontal coordinate system is specific to your location, and no matter where in the earth you are, this is what it looks like in the sky, the coordinate system. Okay. Now let's go and turn on the celestial equator. So we have hidden the celestial equator. Now we are turning it on. The blue line you are seeing here is the celestial equator. Remember, that is the equator of the earth projected onto the sky. It also corresponds to the line of declination 0. It's a great circle. It's the only great circle of fixed declination, and its declination is 0. It does not pass through the zenith. The only place where the celestial equator will pass through the zenith is if you are on the earth's equator. So since Bangalore has a latitude of 13 degrees north, the celestial equator will be offset from the zenith by about 13 degrees. Okay, as we can see here. The numbers on the celestial equator, I don't know if you can see them very clearly. Those are the right ascension. We'll get back to that. Okay, now let me turn off the alt-azimuth coordinate grid and turn on the equatorial coordinate grid. So now the grid lines that we are seeing are lines of fixed right ascension and lines of fixed declination. Okay. So the longitude like coordinate here is right ascension. So these lines that are coming out of the pole here are great semicircles of fixed right ascension. They are RA lines, or RA meridians as we call them. The circles around the pole here, these are circles of fixed declination. None of them are great circles except for the celestial equator, which is the great circle of fixed declination equal to 0. The rest are not great circles. So for example, this line here is the declination 80 circle. This is the declination 60 circle. This is the declination 40 circle, and so on. And this is the 22-hour RA line, 0-hour RA line, 2-hour RA line, and so on and so forth. Okay. So if you look at the pole, so the pole star is slightly offset from the north celestial pole, but here's the north celestial pole. If you look at the altitude of the north celestial pole, in this case it's very close to, it will be exactly equal to the latitude of in this case Bangalore, latitude of the location. Okay, so you can see that the coordinates in my status bar on the bottom right are 12 degrees, 56 minutes, and 58 seconds. Depending on how precisely I put my mouse cursor on the north celestial pole, that is very close to the latitude of Bangalore, about 13 degrees. Okay, but the altitude of the NCP is equal, NCP being north celestial pole, is equal to the latitude of the location. So we went over this. So The other pole of this coordinate system is the south celestial pole. Okay, so that's below the horizon in Bangalore, right? Because we are in the northern hemisphere. Here's the south celestial pole. It's directly it's directly opposite to the north celestial pole. This is south celestial pole. That is north celestial pole. Okay. Note that the celestial equator is tilted. Oh, we already went over this. Okay, it's not directly overhead unless you are at the equator. Now what we will do is we will change the location to a few more places that are at varying latitudes to see how the celestial sphere changes. Okay, so I'll turn on the horizon. Now let us go to Singapore, which is very close to the equator of the earth. Its latitude is about 1 degree. Okay, so in this case the celestial equator is very close to the zenith. So if I turn on the Azimuth grid here, you can see this is the zenith and the celestial equator is very close to the zenith. Okay, similarly the north celestial pole as well as the south celestial pole will be very close to the horizon. Polaris will be barely above the horizon, as we can see here, and if I go to the southern side of the sky, the south celestial pole is just below the horizon. If I were exactly on the equator, the celestial equator would pass through the zenith. The north celestial pole and south celestial pole would be exactly at the horizons. Okay, and we would definitely see Polaris rise and set because it's slightly offset from the north celestial pole. Okay, so the equator is the only place on the planet where we will see the entire sky while being at sea level. So altitude or elevation on the earth does give you an advantage in terms of being able to see below the horizon, but yeah, the equator is where you will see both the southern and the northern sky. Okay, so we have explored Singapore. Also note that the time offset between local time and UT is different because Singapore follows this time zone, which is +8 from GMT, right? So unlike +5:30 in India, it is +8 there. Okay, now let us change location to San Francisco, which is close to where I live. Oops, why did that not work? San Francisco. Yes, okay. So in San Francisco, the latitude is about 38 degrees. So this means that the pole star is at an altitude of about 38 degrees. So the north celestial pole is higher than it is in Bangalore. Okay, similarly, the celestial equator has more tilt. So you see, depending on your latitude, this entire equatorial coordinate grid that we are seeing right now gets tilted equal to your latitude, right? So that the NCP is at this position and the celestial equator is similarly tilted. So you can see now in this location, if I go to the zenith and turn on the Altazimuth grid, you can see that the equator is offset from the Altazimuth grid, the zenith, by a large amount, okay, which is 38 degrees or so. Okay, so that's San Francisco. Now let's go to an even more northern location. In this case, let's go to Alert in Canada, which has a latitude of 82 degrees. Okay, so here you can imagine the north pole, the north celestial pole, is very close to the zenith. Okay, and the celestial equator is very close to the horizon. So you can see that the celestial equator is down here. And let me turn on the Altazimuth coordinate system so we can see that the zenith is the north celestial pole is really close to the zenith, right? So if I were exactly at the north pole of the earth, the north celestial pole would be directly overhead and would be coincident with the zenith, and the celestial equator would be coincident with my horizon, and I would only see over day and night, I would only see one half of the sky, right? I would never see the southern half of the sky. So but I would see the same half of the sky every night. So you will always get to see one half of the celestial sphere, maybe a little more if you have altitude. Okay. So now let's go to the southern hemisphere. Let's go to Sydney in Australia, which has a latitude of minus 34 degrees roughly. Okay, here the north celestial pole will have an altitude of minus 34 degrees, right? Which means it will be below the horizon. Okay. Instead, the south celestial pole will have an altitude of plus 34 degrees, so it will be above the horizon. So here we are seeing the south celestial pole. Similarly, the equator is tilted by about 34 degrees from the zenith. So if I turn on the alt-azimuth coordinate grid, here we are, and the equator is tilted 34 degrees, but it's tilted towards the north, as opposed to the equator being tilted towards the south as in the northern hemisphere. Okay, so similarly we can see that the entire coordinate grid, right, the entire coordinate grid is tilted, but it's tilted such that the south pole is up and the north pole is below the horizon. Okay, so now let us return to Bangalore. Okay, north celestial pole is 13 degrees above the horizon. Now let me turn on the ecliptic line. Okay, so if you see now, this green line that we have added to the map is the ecliptic, and you can see that most of the planets, including the sun, are more or less aligned with that line. Okay, the sun, moon, and the planets, to be precise, are more or less aligned with that line. Especially the sun is pretty much on that line, and that's because we define the ecliptic based on the Earth's orbit, and the other orbits of the orbits of other planets and the orbit of the moon are roughly in the same plane, because the solar system is roughly planar. Okay, so the ecliptic is tilted to the celestial equator at an angle of about 23.5 degrees. Right, that's why they are not coincident, and it intersects at 2 points. One point here, which is marked 0 here, is the vernal equinox. That is the right ascension 0 point, right? So this line is the right ascension 0. Remember, we discussed that the equatorial coordinate grid is set up such that the two reference points are the north celestial pole, which has declination of 90 degrees and undetermined RA, and the first point of Aries, or the vernal equinox, which has a right ascension of 0 and a declination of 0. Right, that's this point, the vernal equinox. On the other side, there is one more intersection. Every pair of great circles intersect at 2 points, and the ecliptic is a great circle, so it intersects the celestial equator at 2 points. The other point is here, and that's the point of right ascension 12 and declination 0. That's the autumnal equinox. Okay, on March 22nd, the sun is very close to this vernal equinox, the 0 RA point, and when in September 22nd, the sun is very close to this point, which is the autumnal equinox. And the sun moves along the ecliptic, not along the celestial equator. Okay, so now that we have done that, let me turn on one more line, and that is the local meridian. Remember, the local meridian is the RA line that is vertically above you. Okay, that's the green line here, the thick green line. This line is the projection of your longitude, the longitude of the observer, onto the celestial sphere. So this is the RA line that passes through the zenith, if we may. So when I turn on the zenith, some geometrical errors because of calculations and plotting, but it passes through the zenith. Okay. So remember, we said that the RA of the meridian is the local sidereal time. Okay. Here the sidereal time clock is showing me that the current local sidereal time is 1 hour and 51 minutes or so. So the RA of this meridian, let me pick a star that is very close to this meridian. You will see that its RA is roughly 1 hour and 51 minutes, right? So when I look at it, here's 1 hour 52 minutes or so, right? So the RA of this meridian, if you also look at the status bar, is 1 hour 51 minutes. So that's the definition of local sidereal time. It is the rightest section of the meridian. As time progresses, so let me speed this up slightly so we can see time progress faster than it actually does. So as time progresses here, oops, that's too fast. Let me get back some of these. Yeah, so as time progresses, now every refresh the time is progressing by 2 minutes. You can see that the lines of RA keep moving as the Earth rotates, right? Because RA lines are roughly fixed in the sky, and so are the deck lines. And the RA value on the meridian keeps changing because that's the local sidereal time. Sorry, the status bar doesn't update very well, but you get the idea, right? Earlier it was 2, now it's about 3 hours. Okay, as you can see, it's between the 2 and 4 meridians. Now it's coming close to the 4 meridian, and the local sidereal time is tracking this change. Okay, so let's continue to visualize the rotation of the Earth. Basically, the RA lines are rotating, the RA meridians are rotating about the north celestial pole, and you can see that here. The entire sky is rotating about these two poles, about the north celestial pole and the south celestial pole, which we cannot see in this location. So just for a change, let me set the location to San Francisco, and you'll see that the north celestial pole is higher, but again the RA and deck circles rotate, the entire equatorial coordinate grid rotates at the sidereal rate around celestial poles, and celestial poles remain fixed. Okay, so that brings us to the conclusion of this part of the demonstration. In the next part of the demonstration, we will do some more visual experiments of looking at sidereal time and so on more carefully.